Bonjour à tous, je m'appelle Marie Evenot, je suis la coordonnatrice scientifique à l'éducation et au rayonnement de l'Institut de recherche sur les exoplanètes, l'iREx, et aujourd'hui j'ai le plaisir d'avoir avec moi Ryan Cloutier, qui est un étudiant au doctorat, qui est co-supervisé par un professeur de l'Université de Toronto et par le directeur de l'iREx, René Doyon. On va avoir une petite conversation ensemble. Ryan parle anglais, donc notre conversation va se tenir en anglais. Hi, Ryan. Thanks for being here.
Hello, bonjour.
Ryan, the Space Telescope test will be launched on Monday. Can you tell us a little more about this Space Telescope and why you're excited about it?
Yeah, so this is an extremely exciting telescope that's going to be launched next Monday. Test the Transiting Exoplanet Survey satellite. And so this satellite is going to go up and reach an orbit somewhere between the Earth and the Moon, and basically scan the entire sky over 2 years, searching for the closest transiting exoplanets. So those are planets that actually, as they orbit around their host star, will orbit between the star and the Earth such that you can actually see the planet block some of the starlight. And when you see that dimming of the starlight, you can infer not only the presence of a planet, but also its orbital period, as you see it go around and come back, and also its size by the amount of light that it actually blocks. And so we're expected to detect thousands of various types of planets, all the way from gas giants to water worlds and ice giants, all the way down to small Earth-like planets around these stars. And again, these are all going to be relatively nearby stars. Most of these stars are going to be much closer than the majority of exoplanets that we know of today, which means that they're going to be excellent targets for follow-up studies.
Great, that's indeed exciting. But if I understood you correctly, the planets that we will find through that method are only the ones that by chance are aligned in such a way that they block some light from their star. But what about the other planets, the ones that they don't hide the light of their star? Can we find them too?
Yeah, absolutely. So it's true that because you need those planets, the orientation of those planets' orbits to be basically edge on in order to see them transit, it's true that only 1 or 2% of planets will actually transit. So what happens to the other 98% of planets? Is there any chance of detecting them? And there is, for most of them anyway. And it's via a method called the radial velocity method or the wobble method. So the fact that you have a planet with a mass orbiting around a star, which also has a mass, there's a gravitational interaction between those two bodies. And so the presence of the planet as it goes around its host star tugs the star back and forth. And so you actually get this periodic wobble that we can actually see in the star. Without actually seeing the planet, you can just look at the star and see it wobble back and forth, and you can infer the presence of the planet, and this time its mass, because the gravitational interaction, instead of the size. And so for planets that don't transit, we can at least get some estimate on what their masses are. And of course, because the majority of planetary systems aren't actually transiting, by using the radial velocity method, statistically, you're going to find closer planets to our own solar system than you will with the transit method. And so again, because these systems are very close, their stars tend to be much brighter, which is again an excellent characteristic when you want to look at the best systems for detailed follow-up studies.
Interesting. That method that you described, the radial velocity method, that requires specific instruments, like specialized instruments. I know you're involved with one of them, 2 of them at least. Can you tell us a little more about that?
Yeah, so just the way TESS is optimized to search for planets in transit, we have purpose-built instruments that do radial velocity. And these are called spectrographs, which means you basically see the light from the star as a function of its wavelength. And so you can see basically the different elements and molecules in these stars, in the atmospheres of these stars. And you can see those lines, those features wobble back and forth. And so 2 new instruments that are going to be some of the best in the world at actually doing these sorts of studies. One is called Spiru, which is a near-infrared, high-resolution spectrograph that's going to be on the Canada-France-Hawaii telescope in Mauna Kea and is currently doing on-sky testing, so we're all very, very excited and should have first light in the next couple weeks anyway, which is absolutely fantastic. And then we have a counterpart in the south called NIRPS, the Near-Infrared Planet Searcher, which is actually on the ESO La Silla 3.6-meter telescope in Chile. And a very similar instrument going to be doing the same type of science. And together these two instruments give you full sky coverage, as one is in the north in Hawaii and the other being in the south in Chile. And with these two instruments, in the next few years, we're going to be looking at the closest red dwarf stars, looking for new exoplanetary systems around those stars. And so when I say red dwarfs, I'm talking about stars that are a factor of a few times smaller than the sun. So they're smaller, meaning they're correspondingly cooler than the sun, but they're actually very abundant. We actually find about 4 times more red dwarfs in the solar neighborhood than we do sun-like stars. So really, plenty of opportunities to find new exoplanetary systems around these types of stars with instruments like SPIRU and NIRPS.
Okay, so that's a very interesting instruments. What was your personal implications with these instruments?
So I started relatively recently in that I joined these teams within the last 2 or 3 years, meaning that the instruments have already started to be being built and tested. And so my goal when I joined the team was to work on the data analysis side. So once these instruments go on sky and start accumulating data, how are we going to analyze it? How are we going to look at the data and actually be able to find these exoplanets? And so this is the sort of work that I started doing in a more theoretical context because, of course, the instruments aren't on sky. We don't have real data. So we have to simulate data. And what are those data going to look like? Because you have signals from planets and you have signals from the star itself. There's intrinsic variability on these stars. You can think of, if you've ever seen images of the sun, they tend to have sunspots on them. And if other stars have similar types of spots or magnetically active regions, this can cause an anomalous radial velocity signal that can be confused with planetary signals. And so in those simulations, I had to include those additional signals and then try and work out some sort of algorithm that can disentangle intrinsic stellar activity from planetary signals. And so in the process of doing this, we actually simulated the entire planet search. So SPIRU is going to look at about 100 stars over 3 or 4 years. And I have to simulate that entire survey. So simulate 100 stars with some statistically significant number of planetary systems and try and tease out the planets from the activity. And those simulations are useful because they allow you to make a prediction on what types of planets SPIRU is going to detect and how many planets you expect SPIRU to detect.
So these planets, they are not known yet. You're trying to figure out what they will be, but the stars are known. These stars are stars that we know are in our solar neighborhood.
Exactly.
Okay,
right?
Great.
So there's many stars in the solar neighborhood, and about 100 of which we're going to look at with SPIRU, and these are the best 100, or the most promising for finding new exoplanetary systems.
And well, when you will detect them, if I understand correctly, you are finding them by observing the star, so you're not seeing the planet at all. So you're not seeing if it's the characteristic of the planet. You're only seeing the wobble of the star that indicates that a planet is orbiting around it. What will we know eventually about these planets? What can we know about these planets?
So the great thing about SPIRU and NIRPS is that you're looking at these red dwarfs, which are again very abundant, which means they tend to be very close to our own solar system, which means that they're bright. And not only that, but because they're close, the angular separation on the sky between the planet and the star.
You mean the actual separation?
The physical separation. So if you wanted to take a picture of this planetary system, how far is the star from the planet? And if you look at nearby systems, you're maximizing that separation. So you imagine if you look at a star that's on the other side of the galaxy, if there was any planet orbiting around that star, it would appear in an image very close to that star. So you wouldn't actually be able to see it because basically the contrast between these planets and stars is like 1/1,billion.
Yeah, the star is much more bright.
Much more bright. And so if we want ever to get to the point where we can image planets that are in some ways like the Earth in terms of their size and possibly even their composition, you have to look at the closest stars to our own solar neighborhood. And so that's what Spiro and NIRPS is going to do. It's going to find the closest planetary systems for which one day we hope to be able to image these systems. And the timing is fantastic because it's going to take a few years for us to initiate the Spiro and NIRPS planet searches, to actually go through the data and find those planets. And then hopefully a few years after that, the next generation of extremely large telescopes are going to come online. And so these are 30, 40 meter class telescopes on the ground that are going to have purpose-built imaging instruments to look at these types of planets, planets that Spiro and NIRPS are going to find.
Great.
And so that, for the first time, is going to give us direct images of planets like the Earth, which with our current technological capabilities, we're nowhere close.
And what do you learn by imaging a planet that you don't learn when you find it through radial velocity or transit?
So this, for the first time, you're going to actually be seeing the planet. Instead of just inferring its presence by looking at the star, you're actually receiving photons from the planet. And so those photons are reflected photons, for the most part, which means that they're stellar photons reflected off the planet and coming back into your camera on your telescope, the same way that we see the moon at night. But there's imprints of the molecular composition of those planets' atmospheres that you see in the reflected photons. And so you can start to infer the presence of chemical species in the atmospheres of these planets. So if this planet has a lot of water vapor in its atmosphere, you might see some excess absorption from water or from oxygen, which would be absolutely fantastic because in our own atmosphere anyway, oxygen in absorption in our atmosphere comes from photosynthesis, from life. So it's what we call a potential biosignature. And that's really the holy grail. That's what you want to find for these types of planets.
That looks quite exciting. So you have a lot of work on your plate for the next years, right?
Yes, absolutely.
Okay, well, thanks for spending time with us.
Thank you.